students, we will just try to relate between the collision theory and the Arrhenius equation. Now, the collision theory stated that the rate of the reaction is going to depend upon the effective collision, right? That is the number of the effective collisions per unit time and per unit volume. That is the collision frequency denoted by capital Z. It will also depend upon the we can say the fraction of the molecules which will undergo the effective collision or which are going to overcome the energy barrier and the orientation barrier. So from the collision theory, if we just try to write down the rate of the reaction for this given bimolecular reaction. So there the rate of reaction will be equal to, it was Z into F. Now students, what is F here? F was the fraction of the molecule which will undergo the effective collision. That is the fraction of the molecule, right? Now, how we can just find the relation here? So for that, we will just express this frequency, right? That is F, that is a fraction. So here, this is the collision frequency of the reactant En B, right? Now we will just express this rate. Now this rate of the reaction, it will be equal to the rate constant also, right? So we will write it in this way because rate constant R, right? It is just the way of expressing the rate of reaction only here. So K equals to ZABF, right? Now from the Arrhenius equation, right student? So here we are going to express the Arrhenius equation, which tell us that K equals to A e raised to power minus EA upon RT. This is the Arrhenius equation where K is a rate constant, A is the Arrhenius factor, and this exponential term e raised to power minus EA upon RT, it is the fraction of the molecule which will which will have the activation energy, that is the minimum energy that is required by the reactant before collision, right students? So here we are just going to relate these two equations or these two concepts together, right? So for that we will have here fraction. Here we are going to just express this fraction as, or we can write it as K equals to Z AB into e raised to power minus EA upon RT, right? So if you just see here that this K equals to A e raised to power minus EA upon RT, here K equals to ZAB into E raised to power minus EA upon RT, right? So here you can just either place this value, that is both rate constants are equating with one another. So if we compare these two equations together, let it be this equation 1 and this is equation 2, right students? So you will just compare those two equations. Now students, if you are comparing it, right, so we have to look it again. Here the rate constant, right, is depending upon the rate constant is related with the activation energy, right, EAB. Now it is not always so that if the molecules have the sufficient energy or they have the energy either equal or greater than that of the threshold energy or the active we can say they have got the activation energy, right, then it might be possible that they don't undergo the collision right in a right way, or we can say that proper orientation factor we have to include here. We haven't included here the proper orientation factor, That is the probability factor here. So it so may happen that the molecules bear sufficiently high energy, right? But they are not able to undergo the product formation. That will be only possible because might be that the molecules are not undergoing the collision in a proper way, so that the old bonds are not broken down and new bonds are not being formed. So to just compensate this, we have to consider here the probability factor. So we will just add it and then we are going to compare the two equations, right students? So here we will add first the probability factor and then we are going to add compare these two equations, right? So I'll be just writing this here, this equation. I'm writing here, it will become now k equals to p z AB into e raised to power minus EA upon RT. Now student, what is P here? P here is the probability factor which is going to consider the proper orientation, right? Now let me make this equation 3, right? Now we will compare equation 2 and equation 3. So students, just compare these two equations. So that is k equals to a e raised to power minus e upon rt, k equals to p z a b into e minus e raised to power minus e upon rt. So what you will find that the equations is almost same. So here we can just get the k, that is Arrhenius factor, as p into z a b, right? So from here we can say that the for the reaction to take place, or for the product formation to take place, the collision theory considers that there should be the effective collision, and that effective collision will depend upon the probability factor, that is the proper orientation, right? And along with that, the frequency of the effective collision, which will depend upon, as we have gone through the Maxwell distribution of energies, that it is going to depend upon the energy factor or the energy barrier, right? So it is explaining the we can say the collision theory explains the rate of the reaction, or we can say that it explains the formation of the product, or explains the rate of the reaction, that it will depend upon the activation energy, or we can depend upon the activation energy, as well as it will depend upon the probability factor, that is the orientation barrier. Now students, we are going to solve the numericals which will be based on the uh, formula for deriving the activation energy, that is log k2 upon k1 equals to EA equals to here EA upon 2.303 R within bracket 1 upon T1 minus 1 upon T2. Now students, you can see on the board that I have written a numerical here. So it is that the rate of the reaction becomes near 4 times when the temperature changes from 298 Kelvin to 313 Kelvin. We have to calculate the activation energy assuming that it doesn't change with temperature. The rate constant, which is the gas constant value which is given to us is here 8.314 joule per Kelvin mole inverse, and log 4 is given to us 0.6021. Now students, here what is given here, that the rate of the reaction becomes 4 times when the temperature changes from 298 Kelvin to 313 Kelvin. So here when temperature is, this is the solution here we are doing, when temperature is 298 Kelvin, at that time let the K1 be K. Now when the temperature is been increased to T2, that is 313 Kelvin, so it will be K2 is getting 4 times, that it is getting 4K, right? Now we will put these equation values in the equation. So here it is log K2 upon K1 equals to EA upon 2.303 R upon 1 minus 1 upon T1 minus 1 upon T2, right? We have got this equation. Now we will put the value. We will get log, what is the K2 here? It is 4K. K1 is here K. It is EA upon 2.303. R is here 8.314. Within bracket we'll write 1 upon T1 is 298 minus 1 upon 313. Right, students? So here K to K will get cancelled and we will get log 4 equals to EA upon 2.303 into 8.314. Within bracket we can write down here 313 minus 298 upon 298 into 313. Now what is the value of log 4? It is 0.602 and it is given to us. 0.6021 will be equal to EA upon 2.303 into 8.314, right? Here we will just subtract 313 minus 298 here. So what we are getting here, we will get here 15, right? So we're putting here 15, 298 into 313, right? You will solve this equation for the activation energy. So it will be 0.6021 into 2.303 into 8.314 into 298 into 313 upon 15. Now students, you will get the activation here, energy here in joule, right? Because we have put the gas constant value here in 8.314 joule per Kelvin mole inverse. So whatever answer you are getting here, it will be in the joule, right? And you have to get it divided by 1000 so that we get the answer in the kilojoule. So here students, we will just do the calculation and we will find out first the activation energy here. Now students, on solving you will get it 71687.25 joule, and as I said you have to get it divided by 1000 so that you get the answer in kilojoule. So you get 71.687 kilojoule per mole, right? This was joule per mole. Now this will be 71.687 kilojoule per mole. Now students, you can just get it rounded up to 4 significant figure also. So that time it will become 71.67, right? Kilojoule per mole. So but most important is here again I am telling, that is don't forget to put the unit, and that is most important, right? If you just forget it, your half marks will be deducted. So in this way you will just solve it by using the equation for the activation energy, which relates activation energy with that of the rate constants at two different temperature, right? So at the we can again just summarize that the collision theory, right? The collision theory just to have the rate of the reaction, right? To occur or to carry on, it relates the effective collision with the that of the proper orientation factor, that is the probability factor, and second is the activation energy, that is the minimum energy required by the reactants to undergo the reaction, right? So you will practice the numericals based on this type.